In this video, we will be talking about polynomial functions of higher degrees. Before we do that, we need to recall a couple of things. First, the definition of a polynomial. F of x is equal to an times x to the power of n plus an minus 1 times x to the power of n minus 1 plus everything in between plus a2 times x squared plus a1 times x plus a0 to the x to the 0. This is a polynomial function where n is a non-negative integer and an minus 1 all the way down to a0 are all real numbers, where an, the leading coefficient, is not 0. This is a polynomial function of x with degree n. So the highest number n, that is our degree. The next thing we need to recall are polynomial functions we know. So we've gone over two parent functions that are polynomial functions. The first is f of x is equal to x squared, and the second is f of x is equal to x cubed. We need to know what the general shape of these are and their behavior. The next thing that we've gone over that we need to recall are shifts, reflections, stretches, and shrinks. Down below is just an abbreviated version of all these rules, and we need to generally know how they work. So what do polynomial function graphs look like? Well, they generally have two things in common. First, they are all continuous. And by continuous, I mean that there are no gaps anywhere in the graph, and they continue on to forever. This is contrary to our non-continuous graph, which has either some gap or they do not continue on into any direction to infinity. The other thing that they share in common is that they are smooth and curved. So again, polynomial functions are always continuous, and there's a general smooth and curved pattern to them. An example of a not smooth or not curved function would be the absolute value function. So anything with an edge is not a polynomial function, and anything that has a gap is also not a polynomial function. Besides being continuous and smooth, polynomial functions generally take on two different shapes. One is that of a parabola, and one is that of something that looks like x cubed. This is determined by the degree, which is the highest exponent in the polynomial. If that degree is even, it will look somewhat like a parabola, and if that degree is odd, it will look somewhat like an x cube. As the degree heightens, the graph will be much flatter toward the origin and will also go up steeper. So for example, if we have f of x is equal to x to the fifth, it will stay flatter near the origin, but it will go up steeper. And then same thing for the cubic. Say we have f of x is equal to x to the seventh. It will be much flatter toward the origin, but will go up at a faster rate. In these higher degree polynomials, the rules of transformation still apply. So for example, if we have f of x is equal to negative x to the fifth, we should know approximately what that looks like. So our degree is 5, which is odd, so it'll look something like x cubed. And then this negative tells us that it's upside down. This is a negative outside of parentheses, which means we flip the entire graph upside down. So it should look something like this. And then next, if f of x is equal to x plus 1 to the fourth minus 3, the first thing we look at is the degree, which is even. So it should look something like a parabola. And then there's a plus 1 on the inside, which means we go left 1. And then negative 3 on the outside, which means we go down 3. So we'll start right there at the vertex. And again, this will look like a parabola, just a little bit wider at its edge, and it'll go up a little bit faster. So it'll look something like that. Whether the graph of a polynomial function rises or falls at its ends can be determined by the function's degree, even or odd, and by its leading coefficient, the coefficient attached to the highest exponent. So the leading coefficient test tells us that end behavior. So as x moves left and right, the graph of the polynomial function rises or falls in the following manner. So if n, our degree, is odd, and our leading coefficient is positive, this will look, again, something like our parent function x cubed. So as x approaches negative infinity as it moves to the left, f of x is also going down. So that also approaches negative infinity. As x approaches positive infinity, as it goes right, f of x is also going up toward positive infinity. If the leading coefficient is negative, we get the parent function of x cubed, but flipped upside down. So as x approaches negative infinity, as x moves left, f of x is going up toward positive infinity. As x approaches positive infinity, so as x moves right, f of x is going down toward negative infinity. And then our second option is when n, our degree, is even. So if we have a leading coefficient that's positive, again, we're going to have something that looks like our parent function x squared. As x moves left toward negative infinity, f of x is still going up toward positive infinity. As x moves right toward positive infinity, f of x is still going up toward positive infinity. And then if we have a leading coefficient that's negative, we're going to get the parent function x squared flipped upside down, or at least something that looks like it. So as x moves left, as x approaches negative infinity, f of x is going down toward negative infinity. As x approaches positive infinity, f of x is still going down toward negative infinity. So for example, say we want to describe the end behavior of the graph of each function. So first, f of x is negative x cubed plus 4x. The first thing we can do here is look at the degree, which is 3, which is odd. Then we can look at the leading coefficient. In this case, our leading coefficient is negative 1. So our degree is 3, which is odd, and our leading coefficient is negative 1. Okay, so now our graph will start up top, and it'll eventually end down below. So f of x will go toward positive infinity as x approaches negative infinity, and f of x will approach negative infinity as x approaches positive infinity. In the second example, f of x is equal to x to the fourth minus 5x squared plus 4. Our highest exponent here is 4, which is our degree, which is even. Our leading coefficient, there is none, so it's assumed to be 1, which is positive. So we will have something that looks like our parent function x squared. So it'll start up top, some things will happen in the middle, and then it'll end up top. So f of x will approach positive infinity as x approaches negative infinity, and f of x will also approach positive infinity as x approaches positive infinity as well. Our third example, f of x is equal to x to the fifth minus x. Again, we look for the highest exponent, which in this case is 5, which is odd. And the leading coefficient, again, there is none here, so it's assumed to be 1. So we have an odd degreed polynomial with a leading coefficient that's positive. So we will look something like this. So it'll start down bottom and end up top. So f of x approaches negative infinity. F of x goes down as x approaches negative infinity. So as x moves left. F of x approaches positive infinity. So f of x goes up as x approaches positive infinity as well. So x goes right, f of x goes up. X goes left, f of x goes down. This is a reminder, the leading coefficient test only determines whether the graph eventually rises or falls. It doesn't tell us anything about intercepts, minimum and maximum, or anything else. That is why there are dotted lines in between. So the red dotted line means we don't really know what happens in between. We only know the top and the bottom. Same with the blue graph. We only know what happens at the extreme. We don't know what happens in between. The next thing we need to do is talk about zeros of a polynomial function. So for a function f of x of degree n, the function has at most n real zeros. And these zeros are where it crosses the x-axis. The graph of f of x has at most n minus 1 turning points. So think positive slope to negative slope or negative slope to positive slope. These are peaked at minimum and maximum, which will be labeled in green. So anywhere there's a change in direction, that's called a relative min or a relative max. When we talk about zeros, any of these 4 things can be used. So x equals a is a 0, x equals a is a solution, x minus a is a factor, or a0 is an x-intercept. All of these things are interchangeable and they mean the same thing. We're just talking about where the graph intersects the x-axis. So let's say we want to graph f of x is equal to negative 2x to the fourth plus 2x squared. And in order to do that, the first thing we can do is check for n behavior. So our degree is 4, because that's the highest exponent, which is even. And our leading coefficient is negative 2, which is negative. So we know that it will end low and start low. The rest of the graph has to do with the zeros. So in order to find those, we can factor a little bit. So the greatest common factor between negative 2x to the fourth and 2x squared, we can pull out negative 2x squared. If we do that, we are left with x squared minus 1. If we set that equal to 0, we're on our way to finding the x-intercepts. This x squared minus 1 can actually be factored a little bit more into x plus 1 times x minus 1. After we get here, then we can set each of these factors equal to 0. So negative 2x squared is equal to 0, x plus 1 is equal to 0, and x minus 1 is equal to 0. When we solve for these, x is equal to 0, x is equal to negative 1, and x is equal to positive 1. So each of these are where our graph crosses the x-axis. So crosses at negative 1, at 0, and at positive 1. So it should look something like this. Again, we know it ends low over here. It goes through the x-axis, and then it has to come back down. And the only way to do that is to touch the x-axis at this middle part. So the final thing we need to go over is the intermediate value theorem. And this definition is a little bit complex, but it's a very simple idea. So let a and b be real numbers such that a is less than b. If f, our function, is a polynomial function such that f of a does not equal f of b, then in the interval ab, so in between a and b, f takes on every value between f of a and f of b. What this does is it helps locate real zeros. So what this says is if we have some input a and some input b such that a is less than b, then f of a and f of b are somewhat apart. But the function has to go through every point on this graph in order to get to the next point. Again, this is used to approximate zeros because graphs can only change signs, so go from negative to positive or positive to negative, if it crosses the x-axis. So if you find a value of x where f of a is positive and a value x equals b where f of b is negative, then there must be a real zero between a and b. So if you start somewhere up here and you find another point down here and it's a polynomial, the graph must go through the x-axis. So you can gradually narrow this margin down in order to approximate the zero. So for example, using all the tools we've just gone over, let's sketch the graph of f of x is equal to negative 2x cubed plus 6x squared minus 9/2 x. The first thing we can do is look at the degree of the polynomial, which is 3, which is odd. And the leading coefficient is negative 2, which is negative. So we already know a couple of things. First, that our graph will start up high and end down low. In order to fill in the blanks, we can do a little bit of factoring and find the zeros. The greatest common factor between all of these things is going to be negative 1/2 x. If we pull negative 1/2 x out of everything, we will end up getting 4x squared minus 12x plus 9. Then if we do a little bit of factoring, we can simplify this even a little bit more. So this 4x squared minus 12x plus 9 ends up factoring to 2x minus 3 quantity squared. So if we set that equal to 0, then we can solve for the x-intercepts. So negative 1/2 x is equal to 0, and 2x minus 3 is equal to 0. So x is equal to 0, 2x is equal to positive 3, so x is 3/2. So if we plot those, we have 1 at the origin and 1 at about 1.5. So now we have a pretty good idea of what our graph is going to look like, but we don't know exactly what happens in the middle still. So then we can use our intermediate value theorem to figure that out. So if we plug in a couple of values, let's say f of 0.5, which is between these 2 points, we know we will have a better idea about what happens. So if we plug that in, we end up getting negative 1, which is negative. So all of the points between this 0 and this 0 have to be below the x-axis, which means this point, it'll come up kind of like that. So if we graph this using what we know, we start up top, go to the 0, go negative, come back up, but then go right back down. So this is just a rough general sketch using the tools that we've just gone over. So as a review, we've gone over several different things, and this is a lot of information, but this is a condensed version of everything that we've gone over. So first, the definition of a polynomial. Second, the graph of polynomials and the rules that they follow. So they are continuous, they are smooth, they generally take two different shapes based on their degree, either even or odd, and their end behavior is determined by their leading coefficient. Again, this is split up into even and odd, and then their leading coefficient being greater than 0 or less than 0. Then we went over zeros and the intermediate value theorem, which basically lets us approximate zeros, or it lets us determine what happens between two zeros in a graph. So again, I understand that this is a lot of information, but all of these things are very important in order to analyze a graph or analyze a function.